In this video, we're going to look at another problem that utilizes Newton's third law. I have a car of 1,000 kilograms pushing a large truck of 4,000 kilograms. The truck is in neutral, and I'm told that there is a frictional force of 800 newtons to the left on it. The car is in gear, and so the motors are trying to turn the wheels which are in contact with the ground. And that contact gives me a frictional contact force on the car of 7,500 newtons to the right. I want to know the acceleration of the whole system and the contact forces between the vehicles. Since I know I want to apply Newton's laws to this problem, I start with Newton's second law, and that requires me to choose one object. So I'm going to start with the car. Isolating it, I now want to find the forces on that car. I'm going to just look in one dimension. I can tell from my system that all of the motion is horizontal. The acceleration in the vertical direction is 0, it will be 0 forever, and so I'm invoking my sort of one-dimensional model that I can ignore any forces in the vertical direction and just look at the horizontal dimension. So there are two forces in the horizontal dimension. There's that frictional force to the right, which I was given, and then now there's a contact force of the truck on the car, which I've indicated by the subscript Tc. And the contact force from the truck on the car then is going to be to the left. So I want to sum these forces, and so I've written them out here. I have the force due to friction on the car. It has some magnitude, and it's in the positive x direction. The force from the truck on the car has some magnitude, and it points in the negative direction. The vector sum of these forces is equal to the mass of that one object, the car, which I've indicated by small m, times the acceleration of the car, which is a vector. It has a magnitude of the mass times the magnitude of the acceleration, and it's going to be in the positive x direction. Since it's the acceleration of the car, I've indicated that with a subscript c. I can extract the scalar relationship from this. The force in the positive direction of friction on the car minus the magnitude of the force in the negative direction, the force of the truck on the car, is equal to the mass of the car times the acceleration of the car. So I don't have enough to solve yet. I don't know what the acceleration is, and I don't know the force of the truck on the car. So that means I wanted to look at a new object and apply Newton's second law to that object. My second object is going to be the mass of the truck. I'm going to look at a free body diagram and identify the forces. I'm again only working in the horizontal dimension. There's going to be the force of the car on the truck, and that's going to be to the right, or in the positive direction I've chosen for this free body diagram. And then there's also the force of friction on the truck, which I was given in the problem, which points to the left, or in the negative direction in this coordinate system. Write out what those vectors are. Contact force of the car on the truck has some magnitude in the positive x. The force of friction on the truck has some magnitude in the negative x direction. The vector sum of those forces is equal to the mass of the truck, which I've indicated by capital M, times the acceleration of the truck I've identified with the subscript t. It's a vector. It has a magnitude of the mass times the magnitude of the acceleration, and from this I can extract a scalar relationship using my notation for one-dimensional vectors. I have the magnitude of each vector, and the sign indicates its direction. The car on the truck minus the force of friction on the truck is equal to the mass of the truck times the acceleration of the truck. All right, do I have enough to solve now? Well, I still have some problems. I have essentially 4 unknowns, because I have the acceleration due to the car and the truck, as well as I have the force of the truck on the car and the force of the car on the truck. Well, the first thing is to identify that those two latter forces are a Newton's third law force pair. The contact force of the truck on the car and the contact force of the car on the truck. So that means their magnitudes are the same, and they point in opposite directions, which we've already seen. So I'll just call that magnitude F. What can I say about the accelerations? Again, given the context of the problem, I know that the objects are going to move the same relative to each other, which means their velocities will be the same and their accelerations will be the same. So I can just replace those accelerations with just A. I've made those substitutions and rewritten my equations, and now I need to solve for F and A. It seems to me, looking at it, if I just add those two equations together, the F's will cancel, and I will get the frictional force on the car minus the frictional force on the truck is equal to the total mass times A. and I can go ahead and solve for A. And now, before I plug in any numbers, I want to know whether or not this makes sense. And it certainly does if I think about what this means physically. This difference is the difference between the frictional forces on the combined truck-car system. And this is the total mass of the truck-car system. And so the difference between the total forces would give me the total mass times the combined acceleration. That certainly makes sense. I can go ahead and plug in those numbers, and I get an acceleration of 1.34 meters per second squared. If I take that first equation, I can solve it for the force. I can plug in those numbers, and I get 6,160 newtons. If I'm asked for the forces themselves, I can then go back to my diagram and note that the force on the car on the truck is to the right, and the force of the truck on the car is to the left. And here's my acceleration